Welcome back, everyone. In this lecture, we'll focus on actually training our model. Let's get started. Okay, here we are back at the notebook. First thing we're going to do is create some variables that you can go ahead and play around with and edit. But the first is how many epochs to train for. And this is something that's going to depend on the size of your text data set, as well as the size of your network, as well as the loss or error being reported back to you per epoch. So I'll go ahead and train this for, let's go ahead and say 60 epochs. And then I will choose a batch size of 100. And then the sequence length for each batch, I would recommend a minimum of 100 characters, regardless of how large your actual sample text is. 100 characters is a good place to start off with. And then for printing purposes, I'm going to have a little tracker that's going to start off at 0. And then the number of characters in my text, so the number of characters, let me scroll down a little bit, is equal to the max of the encoded text plus 1 because of indexing starting at 0. Now it's time for our large training loop. So we'll set the model to train. We'll check if the model is using GPU. So if model use GPU, go ahead and set model to run on CUDA. And recall that when I created my model, I went ahead and set GPU is equal to true. Make sure you review the GPU lectures to understand if that's a good fit for you. So we'll go ahead and say model use GPU. And now it's time to begin our large training loop. So for this, we'll say for I in range epochs, we'll go ahead and set up our hidden state. So we'll say hidden is equal to model dot hidden state. And we'll do this from the batch size. And now it's time to generate batches using our generate batches function that we created earlier. So for xy in generate batches based off our training data, our selected batch size, and our selected sequence length, we'll say tracker, keep adding 1 to it. This is again for tracking / printing purposes. So tracker plus equals 1. We'll go ahead and say x. We'll one hot encode x based off the number of characters. X, recall, is a NumPy array. We need to convert these to tensors. So say that our inputs, say torch from NumPy on x, and then our targets is torch from NumPy on y. And just in case we decided to use GPU, we need to select these tensors and put them on CUDA. So say if model use GPU, go ahead and say, let me scroll down, get ourselves a little more room here. Go ahead and say inputs is equal to inputs on CUDA now, and the targets is equal to the targets on CUDA. That's if we're using the GPU. Then we'll go ahead and reset the hidden state. If we don't reset this, then it would backpropagate through all the training history. So we'll say hidden is equal to the tuple. And here what we're going to say is go ahead and grab the data in the state for state, or excuse me, for state in hidden. And then after that, we'll go ahead and set this up so that we have our model. And during the zero gradient phase, we'll say LSTM output in our hidden state is equal to model forward based off inputs and hidden. Take our loss and set that equal to the output of the criterion, where we have LSTM outputs, and we're setting our targets, but we're reviewing them in the correct format so that it's going to be batch size by sequence length. And we're going to call .long here to actually view this as a long tensor. Otherwise, we sometimes get data type issues. Let me make sure I spelled criterion correctly there. Okay, so we have our LSTM output hidden. We have our loss, the criterion, also ready to go. We'll go ahead and here, in order to get rid of a possible exploding gradient problem, we're going to clip our gradients. And luckily, this is done for us with this clip underscore grad norm, where we simply need to pass in the model parameters, again, some sort of max normalized value, And I recommend just using 5 here. Basically making sure our gradients don't get too large. And then we'll call optimizer step. And once this is done, we'll go ahead and check on the validation set. And this will basically be our reporting. So we'll say if tracker mod 25 is equal to 0, go ahead and say val, or validation hidden, is equal to model hidden state. Based off the batch size, we're essentially repeating all the code we did above. And then we'll say val losses, empty list, and set our model to evaluation mode instead of training mode. And now we're going to generate batches just as we did before, except this time we'll do it from the validation data. So we'll say for xy in generate batches, validation data, batch size, sequence length, same as before. In fact, I'm going to copy and paste this code because it is the exact same as before. Basically grabbing X input targets and checking if we're using GPU. So I'm going to paste that in, make sure my indentation is correct here. Transform these onto CUDA if we're using GPU. And then again, we'll reset the hidden state here, essentially repeating all the same code we did before. So I'll say val hidden is equal to tuple. And here we'll grab the state data for state in val hidden. And then same as before, we have our LSTM output as well as our hidden validation state. Move forward based off the inputs and val hidden. And then our validation loss is calculated based off the criterion of LSTM output compared to our correct targets. So that's targets view, and it's going to be based off the batch size times the sequence length. And to avoid a possible data type error, we'll go ahead and request this as long. And let's keep track of all our losses by saying val underscore losses. I'm going to append val loss item. We can plot this out later if we want to. And then at the end of this, after we run through that for loop, I'm going to reset the model to training mode. And then once I've done that, I'll go ahead and print out some information. I'll print out what epoch I'm on. So it's going to be I. And then I'll also print out what step I'm on. That's equal to the tracker. And then I'll finally print out my validation loss, which is going to be equal to val loss, and then call that item. Go ahead and close off that string. And there we have it. Okay, so let's go ahead and quickly run this and make sure we haven't committed any typos or any indentation errors. I'm going to zoom out just so you can see all the code here. Essentially, setting up our variables, setting up our model to train, grabbing the hidden state, going through generation of the batches, one-hot encoding our X data, getting our inputs and targets. Then if we're using the GPU, set them onto CUDA, grabbing the hidden state, calculating LSTM output, calculating the loss, clipping the gradients if necessary, and then for the validation, we'll go ahead and do this kind of every 25th step. Let's go ahead and run this. Make sure we don't get any errors. And it looks like we got a small typo error, LSTM output. So I forgot to write the T there. So let me go back up here, make sure we add in that T. And we also have PyTorch informing us that the most recent way of clipping your gradients has an underscore at the very end of it. So I'll go ahead and add that in as well. So we'll say clip gradient norm. And the last thing we missed is it looks like I forgot to add in to say loss backward after calculating the loss on the criterion. So we'll go ahead and say here loss.backward, open and close parentheses. Let's go ahead and run this and now make sure it's working. So here we have an epoch 0, step 25, our validation loss. We can see on the next step it's beginning to go down. So I will go ahead and fast forward in time until this is done training. Okay, this has finished training. And if we take a look at the loss as we continue training throughout these epochs, you'll see that we may have trained for probably too many epochs. And you can check this out by notice around epoch 14, it looks like our loss is hovering around 1.29 or 1.30. And nothing really improves as we continue training for all the way to 50 epochs. We're still hovering around 1.3, and we're even increasing to 1.31, which probably indicates overfitting to the data set. Now what you can do is add maybe if statements to basically break out of this training loop depending on how much change is happening from one epoch to the other based off this val loss.item. So you can say something like if you're not decreasing by at least 10% per epoch or 1% per epoch, etc., depending on your data and what you're actually trying to accomplish here, then go ahead and break out of the training. But you can see here, basically, even after like 15 epochs, we're just hovering around 1.3, 1.29. Okay, now we got to make sure we go ahead and save this model. So I'll choose a model name. So we'll say model name is equal to, and what's probably a good idea is in the model name to actually include the parameters that your model used. So if we take a look back up here, recall that our particular model is using 512 hidden layers, or excuse me, 512 hidden neurons with 3 layers. So I'll go ahead and bring this back down, and we can name it something like, in a string, hidden. We could do something like 512, and then underscore layers 3, and then say something like shakes for Shakespeare, and we'll go ahead and just say .net, and then let's go ahead and say torch.save, and we'll say model.stateDictionary, and we'll save it under that model name. So we go ahead and run that, and you always want to be careful that you don't overwrite an existing model, so always be careful when choosing this sort of model name. Okay, so in the next lecture, we'll show you how to load that model as well as generate predictions off of it. I'll see you there.